Hi, my name is Milod Kazerounian, and I'm going to be talking about our work on bringing type annotation inference to Ruby. We'll start with a simple example of a Ruby method called normalizeUsername, taken from one of our benchmarks, the Discourse app. Given a string called username, this method returns the normalized version of that string. And our goal is to automatically generate type annotations like string, arrow, string for this method. Now there are a number of reasons why this might be useful. Types are a universal form of documentation, and what's more, Ruby 3 will for the first time introduce syntax for writing type annotations, which means it'd be really useful to have a system for generating them. On top of that, type annotations can serve as the basis for other kinds of program analysis, like code completion for IDEs. Now the traditional solution to this problem is to use constraint-based type inference. But a key challenge with this approach is that the inferred types are often overly general, making them hard to read and less useful to the programmer. We'll see an example of this in a minute. As a solution, we introduced the system InferDL, a system for inferring more useful type annotations. InferDL extends RDL, an existing Ruby type checker. It works by complementing constraint solving with heuristic type guesses, where heuristics are used when constraints generate overly general types, while heuristic guesses are checked against existing constraints, thereby ensuring soundness. We evaluated InferDL on 4 benchmarks and 6 case study programs, and we found that heuristics helped us generate 22% more correct type annotations compared to constraints alone. On top of that, we also found 6 previously unknown bugs in the process, so we think InferDL is a promising system. Now let's take a look at an example of constraint-based type inference and see why this approach sometimes falls short. At the top we see the Ruby method we want to generate a type for, and at the bottom we're going to build up a constraint graph for the types in this method. Now the first thing we would do is assign type variables for the unknown types in our program. In this case we assign the normalizeUsername method the type alpha, arrow, beta, and we add alpha and beta as nodes in our constraint graph. Next, we would generate constraints on the unknown types in our program. We'll use constraints of the form x less than or equal to y, meaning that x must be a subtype of y, or we would also say x is a lower bound on y and y is an upper bound on x. In graph form, we depict this by drawing an edge from the node for x to the node for y. Now notice that the input to this method, username, must have a method called Unicode normalize. We'll represent this with a structural type constraint on alpha, where a structural type tells us the methods that a value must have. Here's our structural type on the graph. We show the name of the method, Unicode normalize, and these dotted line edges connect to the domain and the range of this method. In this case, we use the bottom symbol to indicate that the method takes no arguments, and we use gamma, a fresh type variable, to represent the return from the method. Finally, we draw an edge from alpha to the structural type to indicate that alpha is a subtype of the structural type. Now, notice that username also has a present method. So, we create a structural type for present, and we draw an edge from alpha to that type. Then notice that we called downcase on the result of Unicode normalize. So again, we create a structural type for downcase, and this time draw an edge from gamma, the return type for Unicode normalize, to that structural type. And finally, because the result of calling downcase is returned, we draw an edge from epsilon, the return from downcase, to beta, the return for our overall method. Now at this point we would typically perform constraint resolution, which involves applying rules like transitive closure to generate new constraints. In this case, our example is so simple that we don't actually have to do anything here, but we'll see an example of constraint resolution in a minute. And finally, we perform solution extraction to generate the most general possible type for a method. By that we mean the least restrictive type on the method's callers. Now by following rules for co- and contravariance of method subtyping for returns and arguments, that tells us the direction to look in for solutions, and the rules are shown at the bottom of the slide here. For arguments, we take the intersection of non-variable upper bounds on the argument, and for returns, we take the union of non-variable lower bounds on the return. We leave out variables from solutions because their bounds should have already been propagated by transitive closure, and because the variables themselves represent unknowns, so they don't add much to a solution. Now let's apply these rules to our example. Notice that alpha has two upper bounds, the structural types for Unicode normalize and present. So the solution for alpha, our argument, would be the intersection of these two structural types. And beta, our return type, only has one lower bound, but it's a variable type, which doesn't go into a solution. So in this case, we can't actually come up with any non-variable solutions for beta. Now notice that these solutions are deeply unsatisfying. The structural types in alpha can be pretty unintuitive and hard to read, and typically don't match what a programmer would actually write. What's worse, the solution for alpha isn't even fully expanded because it contains type variables, and fully expanding it would only introduce greater complexity to the solution. On top of that, we fail to extract any ground term solution for beta at all. So we really wish to do better than this. InferDL does this by incorporating heuristics to generate more useful type annotations, by which we typically mean nominal and generic types. Let's see an example of a heuristic type guess. Looking closely at our solution for alpha, we note that only one class has defined Unicode normalize and present methods at the time that we run inference, and that's the class string. So let's guess the nominal type string as a solution for alpha. We'll do this by adding string as both a lower bound and an upper bound on alpha to our constraint graph, then propagating those new constraints to uncover any inconsistencies indicating our guess was wrong, or to find new solutions in our graph, as we'll see in a moment. So the first thing we would do is add string as a solution for alpha, and then we would transitively propagate string to alpha's upper bounds, which are the structural types for Unicode normalize and present. Now, because string is the subtype of the structural type for Unicode normalize, we look up string's type for this method and find that it returns a string. So, we add string as a lower bound on gamma, the return type for this method. Next, we would transitively propagate string to gamma's upper bound, which is the structural type for downcase. Then we similarly look up string's type for the downcase method, find that it returns a string, and so we add string as a lower bound on epsilon, the return for this method. And finally, we transitively propagate string to epsilon's upper bound, which is beta. Because beta is a return type for our method, this means that we've found string as a solution for beta. So just by applying a single heuristic guess, we were able to generate the type annotation string arrow string for our method. This type is much more concise, easy to read, and probably what the programmer would actually write. Now the guess we just made actually follows a heuristic rule we wrote called struct to nominal. The rule, stated here in English, says that if an argument solution consists of structural types, look up which classes at runtime have defined the structural types methods. If that number of classes is small, then we replace the structural types with the union of nominal types of those classes. And this allows us to replace structural types, which can be hard to read, by nominal types. And now we can define our overall heuristic solution extraction procedure. The first thing we do, as we saw, is extract solutions using the standard constraint solving approach. Next, for overly general solutions, we would run heuristics to try to find better solutions. By overly general, we mean structural, intersection, union, top and bottom types. And you can take a look at our paper for more discussion on why we chose these types. If a heuristic procedure produces a solution, then we add that solution to the constraint graph and run constraint resolution. If constraint resolution resulted in a type error, then we would roll back that heuristic solution, thereby ensuring soundness. And finally, because heuristic solutions can lead to other solutions as we saw, we repeat steps 1 through 4 until no new constraints are generated. Let's take a look at some of the other heuristic rules we used. 6 of the rules we used were based on the names of variables and methods in programs. We present only 3 of them here for brevity. One rule, called int names, says that variables ending with count, id, or num should get the type integer. The predicate method rule says that the return type for methods ending with a question mark should get the type Boolean. And the isModel rule is applied only to Ruby on Rails apps. It says that variables with the same name as a Rails model class, which is a special type of class that maps to a table in the database, should get that class as its type. So for example, a variable called user would get the nominal type user if such a class exists. And you can check out the paper for our 3 other name-based rules. Finally, we used a rule for generating precise hash types, which turns structural types for hash accessing and writing methods into the corresponding finite hash type, which is RDL's precise version of a hash type. For example, if we had the structural type which said that we wrote to the key name with a string, we would turn that into the finite hash type shown here, which says that we map name to string. And you can find much more detail on our inference system in our paper. We discuss how to express heuristics using configurable anonymous functions, which means that heuristic rules aren't actually baked into the type system, but rather that the programmer can pick and choose what heuristics they wish to use. We provide a formal description of our inference algorithm. We discuss the handling of types for third-party library methods. We talk about how to infer types for global class and instance variables. And finally, we discuss choice types, which are an approach to type checking overloaded methods. We evaluated InferDL by running it on 4 Ruby apps, which had previously been used as type checking benchmarks. This means that these apps had existing type annotations, which we could use as gold standard target types to be inferred. The results of that evaluation are shown in this table. The first column gives the number of methods we ran inference on for each app. In total, we ran inference on 250 methods across these apps. The meth types column separately counts the number of argument and return types we aim to infer. By separately counting these, we're able to more precisely track InferDL's performance. The var types column gives the number of instance, class, and global variable types we aim to infer, and the total types column sums the previous 2 columns. So in total, we aim to infer 496 individual types. The next column shows the number of typecasts we had to write to avoid false positive type errors. In total, we had to write 13 casts to avoid such errors. Next, we show the inference time when using versus not using heuristics. When using heuristics, inference took about 32 seconds, while when not using heuristics, inference took about 9 seconds. When we took a closer look, we found that about 75% of the time spent on inference when using heuristics was spent on just a single rule, struct to nominal, which involves searching the space of all methods defined for each class in a program. Now, even though we were able to achieve some speedups using pre-processing and caching, this nevertheless remains an expensive computation. Next, we show the number of correct types we were able to infer when using versus not using heuristics. By correct, we mean exactly as the original gold standard type or a subtype of the gold standard type. For this latter category, we used manual inspection to make sure that the inferred type was sensible. Our key finding is that heuristics helped us to infer over 100 more correct types than not using heuristics, or about 22% of the total number of types. This indicates that heuristics really are useful for inferring types that a programmer would actually write down. Finally, we show the number of uses for the struct to nominal, name-based, and hash heuristics. Clearly, name-based heuristics were the most useful for this group of apps, having been used 193 times during inference. In addition to running on the 4 benchmarks we just saw, we also ran InferDL on 6 additional case study programs for which we did not have gold standard type annotations. We omit the detailed results here, but our key findings were that in some cases, heuristics can actually lead to lower overall inference time, and we also found that the struct to nominal heuristic rule was significantly more useful for these programs. You can find more detailed results in the paper. And finally, when running across these 10 programs, InferDL found 6 previously unknown bugs, all of which were confirmed with the developers. These bugs consisted of undefined variables, methods, and constants. This indicates to us that not only is InferDL useful for generating type annotations, but also for finding bugs in programs. In conclusion, we implemented InferDL, a system for bringing type annotation inference to Ruby. It works by combining constraint solving with configurable heuristics to generate more useful type annotations. We evaluated InferDL by running it on 4 benchmarks and 6 case study programs, and we found that heuristics helped us to generate more useful type annotations, and we were able to discover 6 previously unknown bugs in the process. So we think InferDL is a promising step towards bringing type annotation inference to Ruby.